next we will be looking into another microprocessor which is slightly more complex compared to 8085, which is the next family of microprocessor from Intel known as 8086. So, the first 8086 process first 16-bit processor. So, 8086 is the first 16-bit processor. So, internal processing is all in terms of 16-bit data, unlike 8085 where it was all 8-bit operation. So, here all the operations are 16-bit operations. So, it was originally released by Intel in 1978. It was designed on HMOS technology, but later on it was upgraded to HMOS 3 technology. So, it has roughly 29,000 transistors. It is a 40 pin dual inline package. So, I like 8085 only. It has 5 volt power supply, does not have internal clock. So, this external asymmetric clock source with 33% duty cycle. So, you have to connect the clock from the external source. So, unlike 8085 where you can just connect a crystal and it acts as it can generate the clock internally. In 8086 that is not possible. So, you have to give clock signal externally with 33% duty cycle means 33% of the time the clock signal is high and 67% of the time the clock signal is low. 20-bit address. So, address bus in case of 8085 was 16-bit, in case of 8086 it is 20-bit address. So, naturally you can access address up to 2 power 10, that is 1 megabyte of memory space. So, addressable memory space is organized into 2 banks of 512 kilobyte each. So, one is the lower bank that which is the even or lower bank and odd or higher bank. So, address line A0 can be used to select even bank and control signal BHE bar is used to access the odd bank. So, these are special signals that are available. So, that way we can divide this memory into 2 512 kilobyte blocks. So, there is a 16-bit address space for the IO mapped devices. Unlike 8085, we had 8-bit IO address. So, here we have got 16-bit IO address. So, total number of IO devices that can be connected is to power 16, that is 64 kilo. So many addresses are available. So, you can connect so many devices. Another important thing that this 8086 has is that it operates in 2 modes. One is known as minimum mode, another is known as maximum mode. So, minimum mode operation is more or less similar to 8085 type of operation, where this processor happens to be the master and you can connect a number of you can connect memory chip and other peripheral devices to it. However, in many systems what is required is that we have multiple masters. So, they coordinate between themselves to get some operation done, get some job done. So, that is the maximum mode of operation. So, there is a pin called min max bar. So, if this pin is equal to 1, so the system will operate in minimum mode, and if it is 0, then it will operate in the maximum mode. So, as usual we will be starting with the pins and signals. So, we have got this AD0 to AD15, which is bidirectional address data bus. So, this AD0 to AD15. Okay, so these are the address data bus, multiplexed address data bus. So, just like in 8085 we had got this lower order address bus was multiplexed, here entire address data bus is multiplexed. The AD lines are used to transmit memory address. The symbol A is used instead of AD, for example, A0 to A15. So, when data is transmitted, so we will be reading as D line. So, AD D0 to D7, D8 to D15 or D0 to D15 like that. So, the rest of the, since this is a 20-bit address space as we said, so total 20 address lines are necessary. So, this AD16 to AD19, so though they are written as AD, but you can better read them as A16 to A19, because there is no data bus line like D16, D17, D18, D19. So, data bus is 16-bit only, it ends at D15. So, you can better read them as A16 by S3. So, they are also multiplexed, but it is multiplexed with the status lines S3, S4, S5 and S6. There is another signal which is BHE bar, which is bus high enable or the S7 is the status, BHE stands for bus high enable. It is used to enable data onto the most significant half of the data bus. So, D8 to D15. So, when we want to say that we have got this the data is available on the higher order data bus D8 to D15, in that case this BHE bar signal will be low, telling the process device which is connected to D8 to D15 that data is available there. So, this that's what is written here, that 8-bit device connected to upper half of the data bus can use this BHE signal which is active low, and it is multiplexed with the status signal S7. So, BHE bar is multiplexed with S7. Then there is a min max bar pin. So, this one pin number 33, min max bar pin. So, it will indicate whether the processor is in minimum mode or in maximum mode. Then there is a read bar line which is active low. So, it is when it is doing a memory read or IO read type of operation, then this read bar line will be low. There is another important line which is known as test. So, this test line. So, test bar pin is used tested by the wait instruction. So, sometimes what happens is that while there are multiple there are many operations that are going on in the system. So, we need to wait for some event or some particular operation to be over. So, in that case we can, the processor 8086 has got a special instruction for called wait, and what this wait instruction does is that it suspends the operation of this processor till this test bar line becomes is made low. So, this 8086 will enter into a wait state after execution of this wait instruction, and will resume execution only when test bar is made low by some active hardware. So, that way it is this is the there is read bar, there is a ready signal. So, ready signal is used for external memory can tell whether some device is slow or not, then it will be the ready signal. So, it will extend the memory operation. Then there is a reset signal which causes the processor to immediately terminate its present activity. So, just like 8085 reset signal, the signal must be active high for at least 4 clock cycles to be acknowledged, because if it is not so, then maybe it is a very small amount of time and the reset was actually not intended, just a spike came. So, just to avoid that situation, so it is kept, it is required that the reset should be active for 4 clock cycles. Then the clock, we have already said the clock will provide the basic timing for the processor operation and bus control activity. Asymmetric square wave with 33% duty cycle. So, it is like this. So, this is the 33% of the time the clock signal is high and 67% of the time the clock signal is low. So, it is like this. So, if this is the total time period from here to here, so this is the 33% and this is 67%. So, 67% the signal should be low. Anyway, so that is how this clock signal should be provided. Now, there is one interrupt line, unlike 8085 where we have got a number of interrupt lines. So, here we have got only one INTR pin which is interrupt request. So, this is a triggered input and sampled during the last clock cycle of each instruction to determine the availability of the request. So, as true for 8085 also. So, this interrupt line is sampled on the last clock cycle of an instruction execution. So, that way it decides whether the interrupt has arrived or not, and if an interrupt has arrived, so it will go into an interrupt acknowledge cycle. So, coming to this min max pin. So, this min max pin there are two modes of operation for 8086, one is known as minimum mode, another is known as maximum mode. So, minimum mode is just like a single processor system. So, in minimum mode of operation, the microprocessor do not associate with any co-processors and cannot be used for multiprocessor system. So, if there are multiple processors, so we get a multiprocessor system. Many times this 8086 it can connect some co-processor with it. For example, there is a very well known co-processor 8087 which is a math co-processor. So, that whatever mathematical operations are required, so 8086 will transfer those instructions to 8087 for execution. That way operation can be made faster. So, while doing those operations, the co-processor also needs to access the memory and other devices. So, we have to give the control of the bus to that device in that case, or to that co-processor in that case. So, in minimum mode of operation, so this is not possible. Okay. So, here in the 8086 itself is the sole master of the whole system. The maximum mode of operation, so it can 8086 can work in multiprocessor or coprocessor configuration, and minimum maximum mode is configured by this min max bar pin. So, this min max bar line being equal to 1, so it will mean it is a minimum mode, and it is equal to 0, so it is a maximum mode of operation. So, minimum mode signals. So, these are the important signals that we have in minimum mode of operation. One is DT R bar. So, DT R bar is data transmit or receive. So, this is output signal from the processor to control the direction of data flow through the data transceiver. So, if it is using some asynchronous transfer, then this DT R bar can be useful. Then DEN bar, data enable. So, this is output from the processor as output enable for the transceivers. So, these are actually for serial transmission. Then ALE, so this is address latch enable. So, this is for demultiplexing the address and data bus for using external latches. Then M by IO bar. So, in case of 8085 we have IO by M bar. So, here it is the name is the convention is just reversed. For memory access, this M by IO bar line is equal to 1, and for IO access this M by IO bar line is equal to 0. And then we have got this write bar, write control signal. So, it is asserted low whenever processor writes data to memory or IO port, and there is INTA bar line. So, it is interrupt acknowledge. When the interrupt request is accepted by the processor, the output will be low. So, that way that acknowledge signal will go to the device, and device will know that the processor has gone into an interrupt acknowledge mode. So, it will provide the interrupt service routine address. Some more minimum mode signals, there is a hold signal. So, basically this is for relinquishing the control of this data and address bus. So, there is a mode of transfer which is known as DMA, direct memory access, where this another bus controller, it is used for transferring the content directly from memory, one memory location to other memory block transfer, or from IO device to memory. So, like that. So, this DMA controller, it has got a number of secondary devices connected to it, and then through this DMA controller. So, we can transfer data blocks from these IO devices to the memory without any intervention of the processor. So, this for that purpose the processor 8086 needs to release the control of this address and data buses, and for that we have got this hold and hold acknowledge lines. So, if a request comes on the hold signal, hold line, that means the processor will understand that some other master is asking for bus access. So, it will be giving this hold acknowledge. So, it will release the control of the bus, and it will be asserting this hold acknowledge line. So, that way this the requesting processor will understand that okay, this hold has been granted. On the other hand, for the maximum mode of operation, so this min max bar line has to be grounded, and this status signals S0, S1 and S2, they are used by 8086 bus controller to generate bus timing control signals. These are, so the decoding is like this, if it is 000, so it is interrupt acknowledge, 001, so read IO port. So, like that. So, that way this is actually giving some information about what is the mode, what is the operation that this 8086 is doing now. So, the status lines gives that indication. There are two more signals, QS0 bar and QS1 bar. So, they are Q status. So, we will come to this Q slightly later. So, what happens is that internally 8086 possesses one instruction Q, and in that instruction Q all the instructions, when they are fetched from from the memory, so they are kept. Okay. So, that speeds up the operation of this processor. So, we will see that. So, what is the status of that Q? So, that is actually indicated by this QS0, QS1 lines. So, if it is 00 means Q is no operation is being done on the Q. If it is 01, so it is the first byte of an opcode from the Q has been taken. 10, the Q is empty, and 11, it is a subsequent byte from the Q. So, these are the various Q operations that are taking place. So, this is the processor gives this indication to the outside. So, the external device can track the internal status of this 8086 Q by means of these lines. Then this RQ and GT lines, so bus request and bus grant lines. So, these are used by other local bus masters to force the processor to release the local bus at the end of the processor's current bus cycle. So, this if a device, just like in minimum mode we had the hold and hold acknowledge lines. So, in maximum mode we have got this request and grant lines. So, any processor which is asking for this bus access, so it will give a request on this request line, and getting this request, if the processor will finish the current bus cycle. So, whatever it was doing, so that cycle is finished, and then the bus is released. So, when the bus is released, then this corresponding grant signal is given. So, we have got two lines RQGT0 and RQGT1. Out of these two, GT0 has got higher priority than GT1. So, if you have got one device connected to GT0, another device connected to GT1, so GT0 device will have more priority. So, in this way I can connect a more than one processor, like it may so happen that we design a system like this. So, we have got 3 8086 processors, okay, 3 8086 processors, and then they are all accessing the same memory. The memory part is same, and they are feeding they are controlling this memory by means of this address and data lines. So, it is like this. Now, whenever any processor needs to access the memory, so it has to tell the other processors that I need to access it. So, it may be this is connected over this RQ0 line, and this is connected over RQ1 line. So, if this is the main master, then when this fellow needs to use the bus, so on RQ0 line it will send a request to this. Accordingly, if it is granted, then this processor will be allowed to access this memory. This bus will be controlled by this first processor. On the other hand, if this device needs this processor needs to use the bus, then it will send a request on this RQ1 line, and if it is granted, then it will be using the bus by this line. So, this is how this request and grant lines will work, just like this hold and hold acknowledge in case of minimum mode of operation. So, there is another pin which is known as lock bar pin. So, this is an output signal activated by lock prefix instruction. So, lock prefix instruction means that we will see that there are some instructions in 8086 where you can put a lock prefix. So, you can write lock in front of them. So, it means that it will remain active until the completion of the instruction prefixed by lock. So, this the 8086 output low on the lock bar pin while executing instructions prefixed by lock to prevent other bus masters from gaining control of the system bus. Like if suppose in the previous example that we took, so we had 3 8086 processors. So, when one processor is trying to request for the bus from another processor, so first instead of sending the request directly, it may check the lock bar pin of the other processor. So, if that lock bar pin is 0, that means the processor is executing some lock type of instruction, where lock prefixed instruction, where it will not release the bus because then the memory content may become inconsistent. The reason is that if I am if there is a memory location, if there is a memory location like this, say if this is say the memory, and then there is one location and we have got two masters, master 1 and master 2, and both of them want to modify this location. Now, naturally, so this is a serious condition, because if the modification is not done completely by one processor, then other fellow may write something and the original content will be lost. So, that may lead to some inconsistent state. So, this is a very important problem when we consider the operating system design. So, what is done is that this updation, the writing onto this location, so that instruction is prefixed by a lock part. Okay. So, that as a result, if M1 is executing this, so this M2 while requesting for the memory, so it will first see the lock line of this M1, and if this lock line is low, that means it will not be allowing to access to access the buses. So, it should not send the request lines. So, that is the purpose. So, we can use it for this lock type of instructions. So, Next, we will be looking into the internal architecture of 8086 and how does it differ from 8085. So, internally this 8086 can be divided into two distinct modules. One is known as execution unit, another is known as bus interface unit. So, in the execution unit is the portion where it actually does the execution of the instructions. So, this actual operations are carried out in this part. So, we have got say so in this part we have got a set of registers AX, BX, CX, DX, SP, BP, SI, DI. So, these are few registers that we have here, and out of this AX is a 16-bit register. So, all these registers are 16-bit registers. So, they are called general purpose registers or GPRs, and this AX, BX, CX, DX. So, they can be divided into two parts, high and low, like A high, A low, B high, B low, like that. This SI, DI, SP, BP. So, they are having some special purposes. So, we will come to that later. Then this is the ALU which will be doing the operation, and there are temporary registers from which this ALU input is fed. So, this data bus is 16-bit data bus and this ALU is a 16-bit ALU. So, it can do the operations 16-bit operations. So, you can get the operands from these registers, or you can get the operands from outside through this bus, and that way it will be coming to this ALU. So, there is a control system. So, that will be controlling the operation that this ALU does, and the outcome of the ALU operation. So, that is by in terms of some flag registers. So, flag bits may be set here. So, that may be that may be checked by subsequent instructions and all. So, this EU it will execute instructions that have already been fetched by the bus interface unit. So, if you remember 8085, so what was happening is that one instruction is fetched, then it is decoded, then it is executed. So, it was going in a cycle like fetch, then decode and then execute, and after the execution of the first instruction is over, then only the second instruction is fetched. So, it was going like this. In case of 8086, so this structure is a bit modified. So, where there is this fetch part and decode part. So, they are this fetch part particularly. So, that is separated into a different module. So, we have got this bus interface unit. So, which will fetch the instructions and data from the memory for IO operation, IO ports, writing the data. So, they will be done by this bus interface unit. And in this bus interface unit also, so we have got a few registers CS, DS, ES, SS and IP. So, they are all 16-bit registers. There are some internal communication registers. So, that is internal, not visible to the programmer. There is an address generation unit. So, this so that takes two 16-bit values and performs a 20-bit addition. So, result of this this ALU is a 20-bit ALU. So, it will be producing a 20-bit output, and that 20-bit address goes via this bus control logic to 8086 bus. Okay. So, and internally there is a queue, there is an instruction queue. So, whenever we are doing some operation in this part, so this buses are this bus is free. So, at that time this bus interface unit it fetches subsequent instructions from the memory, and once the instructions have arrived, so they are kept onto this queue. So, this is a 6-byte queue. So, subsequent bytes are fetched from the memory and they are kept into this queue. So, this helps in some amount of overlapping of this fetch, decode, execute phase. So, we have got some overlapped execution of. So, it is a fetch, decode, execute overlapping. So, this is a very important concept that you will find in later processors also. It started with 8086. So, we next we will be looking into detail like what is going to happen. So, we will start with the bus interface unit. So, as I said that this address generation is done by a 20-bit address. So, this 20-bit ALU. So, this will generate a 20-bit address, and this CS, DS, ES, SS. So, they are all 16-bit registers. So, they are called segment registers. CS is called the code segment register, DS is called data segment register, SS is stack segment register, and ES is extra segment register. So, we will be looking into more detail of these segment registers and how are they generating the address. So, these are the segment registers CS, DS, ES, SS and ES, and then you can like if you look into a code, then any program. So, if you look into any program, that program can be divided into the different parts, like we have got the code part, we have got the data part, which is this data can again be divided into global data and local data. Now, for any program, this code part is they are unchanged, okay, they remain same, and this data, the global data and local data. So, normally this local data is created onto the stack, and this global data is put onto the main memory. All are part of main memory, but they are they are allocated at the time of this program loading itself, this global data, and local data is as you are making procedure calls, this local data is filled up. So, we have got these segment registers, and you can divide this physical memory into a number of segments, like say this segments like say 0000 to 2008, then 40. So, we are divided into a few segments. Now, you can name these segments, like say this is segment 0, this is segment 1. So, that way, so this segment actually this is yeah. So, this is segment 0 and segment 1. So, this is a continuous segment, then this segment 2 and 3. So, that way we can think of the memory to be organized into a number of segments, and once we have done that, for this code may be located in segment 0, data may be located in segment 3, stack may be located in segment 4. So, like that we can control in which portion of the memory which part of the program will be loaded. So, this is this facility, this segmenting facility is available in 8086, and so the total 1 megabyte of memory, it is divided into segments of up to 64 kilobytes each, and this it can directly access 4 segments of 64 kilobytes. So, to this 256 kilobytes can be accessed by this any program by 8086 at a particular time. Okay. So, how does it access? So, program obtain access to code and data in the segments by changing the segment register content to point to the desired segment. So, if I say that the segment 0 will be corresponding to the code, then the CS register will be made to point to segment 0. Similarly, if I say that segment 4 will be the data segment, then this DS register is made to point to segment 4. So, each segment is 64 kilobyte. So, I have got at most 4 segments. So, at any point of time, so you can have total 256 kilobyte of space accessed by 8086, and of course, you can change the content of this segment register or all the segment registers to have more number of segments, like at some after some time if you find that DS should better point to segment 3. So, you can change the content of DS. So, segment 3 becomes the data segment. So, that is possible. So, this code segment register is a 16 bit register. So, this is it contains the base or start address of the current code segment, and IP contains the distance or offset from this address to the next instruction byte to be fetched. So, what happens is that this address, when it is formed, so this address is formed as so this address is formed as 16 into the code segment value plus the instruction pointer value. So, whatever so if this is the memory and I have initialized the code segment to be equal to this, and say the address is increasing in this form. So, this is the code segment. So, CS register points to the first one. So, this value, this location's address is in CS register, and the IP value is made equal to 0 say. So, when I am accessing first location, so this 16 into CS plus IP, so it will be accessing this location, then IP value will be incremented in subsequent accesses. So, it will access these locations. So, this IP contains the offset and this CS contains the base value. So, that way this access will be done by the code segment register.